Today we will learn the conditional and biconditional connective and the propositional logic laws. To begin with, what are conditional statements? Conditional statements are denoted by the implies sign. This is called the implies sign. Suppose P stands for it is raining and Q stands for it is cloudy. Now the statement P implies Q basically means that if P occurs, then Q also occurs. That means if it is raining, then it is cloudy. What we need to understand here is that P is a sufficient condition for Q, and Q is a necessary condition for P. Now, what are sufficient and necessary conditions? A condition is said to be a necessary condition if without the occurrence of that condition, the result cannot occur. For example, it cannot rain without it being cloudy. So, Q is a necessary condition for P. However, a sufficient condition means that if P has occurred, then undoubtedly Q has occurred as well. That is, it has rained is sufficient to establish that the weather was cloudy. However, a necessary condition does not necessarily imply that the outcome has occurred, because it has happened many times that the weather was cloudy but it never rained. So, in case of a necessary condition, the outcome is not guaranteed, but for the outcome to occur, the condition is quite necessary. However, in case of a sufficient condition, the outcome is very much guaranteed and the outcome is sure to occur if the first statement has occurred. That is, again, for it to rain, it is necessary that the weather should be cloudy. But if the weather is cloudy, it does not always mean that it will rain. It might happen that it does not rain. So the outcome is not guaranteed. But in case it has rained, then it is very much obvious that the weather was cloudy. So in this case, we have a guarantee that because it rained, then it is quite obvious that the weather was cloudy. Now that we know sufficient and necessary conditions, we can write the conditional statements where P is always the sufficient condition for Q and Q is always the necessary condition for P. Thus, P implies Q in this case means if it is raining, then it is cloudy. This is how a conditional statement is supposed to be written. Now, there are many ways of writing the conditional statements. P implies Q can be written as if P, then Q. It can also be written as P implies Q, Q if P, P only if Q. P is a sufficient condition for Q and Q is a necessary condition for P. That is, in our previous example can be interpreted as if it was raining, then the weather was cloudy. Rain implies cloudy weather. The weather is cloudy if it was raining. It was raining only if it was cloudy. It was raining is a sufficient condition for the weather to be cloudy. The weather was cloudy is a necessary condition for it to rain. That is how the same statement can be written in 6 different ways. Now on to the biconditional statements. The biconditional statement is denoted by the sign this, the logical equivalence sign. It is read as if and only if or if. In mathematics, if and only if is written as if with a double F. Now, suppose there are two statements P and Q. I'm sorry, the sign is this. There are two statements P and Q. They are said to be a biconditional statement only if we can write it as P implies Q and Q implies P. That is, in case of a biconditional statement, P is both a necessary and sufficient condition for Q. Similarly, Q is also both a necessary and sufficient condition for Q. Only then can we say that these two statements are biconditional statements. Now, what is the truth table of a biconditional statement? Let us consider this. Like before, they can be true together, false together, TFFT. When are they biconditional? P if and only if Q. That means P will occur only if Q occurs and Q will occur only if P occurs. Here, both of them occur together. So the condition for P if and only if Q is satisfied and hence it is true. Here, both of them do not occur together, which means that P does not occur if Q does not occur and Q does not occur if P does not occur, which indirectly means that P will occur if Q will occur and Q will occur if P will occur. Hence, this is also true. Now, here P is true but Q is false. Thus, if P occurs, Q does not occur. Hence, the biconditional condition that is required in our case is not satisfied, thus it is false. Similarly here, P does not occur even though Q occurs and again it is false. Thus we find that biconditional statements can occur only if the components that make up the biconditional statements, which are P and Q in our case, are either true together or false together. That is, their truth values should always be the same. Only then can we say that the statements are biconditional statements. Now, suppose this sentence is given to us, the picnic will be cancelled if and only if it is either windy or raining. We are to write this in the form of a biconditional statement. Firstly, we break up the propositional statements. The first propositional statement is this: the picnic will be cancelled. Let it be denoted by P. P denotes the picnic will be cancelled. The second propositional statement is it is windy. This is the second one. This was the first one and now this is the second one. It is windy. Let W denote it is windy. And what is the third statement? Propositional statements. It is raining. This is the third one. Let it be denoted by R. It is raining. Now how can we write this in the form of a biconditional statement? The picnic will be cancelled if and only if it is either windy or raining. Remember to put the brackets here, otherwise the meaning of the statement will obviously change. So this is how we can translate a sentence in the form of a biconditional statement. Thus, we are done with conditional and biconditional connective, and now we can move to the logic laws, which will basically use all the possible logical connectives that we have used till now. So the first logic law that we are considering is De Morgan's law. This law also exists in sets. Now, what is the De Morgan's law? It is also denoted by DML. There are two De Morgan's law. Negation of P or Q is logically equivalent to not P and not Q. And the second one is negation of P and Q is logically equivalent to not P or not Q. This can be proved with the help of a truth table. Let us prove the first one. P, Q, the two basic components that we need. True together, false together, TF, FT. Now, we need P or Q. So, true, false, true, true. Now we need negation of this one, negation of P or Q, which is just reverse the truth values. Now we need negation of P. Again we just reverse the truth values. Negation of Q. Now we need negation of P and negation of Q. The AND connective is here. False together, so obviously they are not true together, so they are false. Both of them are true together, so they are true. One is false in both these cases, again it is false. Now the two statements that we are considering are this and this. We see that they have the same truth values irrespective of the truth values of their components, so they are logically equivalent, and thus we arrive at the De Morgan's law. Similarly, we can use the truth table to prove the second De Morgan's law. Now we move to our second law, which is the commutative law. It is also of two types. The first one being P and Q is logically equivalent to Q and P. And the second one being P or Q is logically equivalent to Q or P. This is quite a lot of common sense here, but we can still prove it with the help of a truth table. P, Q, P and Q, Q and P. This is a quite easy truth table, and I'd like to leave it for the viewers. So this is basically the commutative law that we just did, which can also be proved quite easily with the help of a truth table. We move to the third logical law, which is the associative law. What does the associative law state? P or Q or R is logically equivalent to P or Q or R. And the second one is P and Q or R is logically equivalent to P and Q and R. Sorry, this will be and. These statements P, Q and R. So the truth table will be a tad bit more complex. So I'm going to show it to you. So the truth table for the associative law is P, Q, R. There's a slight trick that we will use here. Firstly, we will do like we normally do for P and Q. True together, false together, TF, T. Now we will rewrite this. True together, false together, T, F, F, T. Now for the first 4, we will assign a truth value to R. For the next 4, which is this, we will assign a false value to R. This way we get all the possible combinations that we can have for 3 statements P, Q and R, which are 8 combinations in our case. So the number of connective, in case there are 4 statements, then so there's a formula to find the number of statements that we will, that the number of truth values that we can have. For 3 statements, the number of different truth values possible is 2 to the power 3, which is 8. If the statements were 4, in that case the number of truth values, the number of possible truth values would be 2 to the power 4, which is 16. So basically the formula is 2 to the power n, which tells us the possible truth values, and we can then verify the number of the number of possibilities we are getting with the formula and see if our answer is correct. What is P or Q in this case? True, both of them are false, one of them is true, true together, false together, one is true. Now what is Q or R? True together, one is true, one is true, true together, one is true, false together, again false together, and one of them is true. Now we need this statement, which is P or Q or R. That means we need to consider this table and this one. They are true together, one of them is true, true together, one is true, again they are true together, false together, one of them is true and one of them is true. Now we move on to the second conditional, which is this. So we need to consider this one and this one, which is true together, one of them is true, true together, one is true, false together, and one of them is true. So we find that the truth values of these 2 statements are always the same, irrespective of the truth values of their components. Hence we can say that these 2 statements are logically equivalent, and thus we arrive at the associative law. This way we have proved the associative law, and now we move on to our the 4th logic law, which is the idempotent law. Now what does the law state? It is again of 2 types. P and P is logically equivalent to P, and P or P is logically equivalent to P. The law is quite obvious, but we can still prove it with the help of a truth table. What are the 2 truth values that P can have? It can either be true or false. What is P and P? Obviously it's TF. And what is P or P? Obviously it is again TF. So these 2 statements are logically equivalent and we get the idempotent law. Now we move on to the 5th logic law, which is the distributive law. What does the distributive law states? It is again of 2 types. P and Q or R is logically equivalent to P and Q or P and R. And what is the second one? P or Q and R is logically equivalent to P or Q and P or R. Now, just like we prepared the truth table for the 3 conditionals P, Q and R, we can again prepare the truth table What will be the headings in the case of this truth table? They will be P, Q, R, Q or R for the first one, Q or R, P and Q, P and R, and finally P and Q or R, and lastly this, the second one. We will see that if we make the truth table for this, we will see that the truth values of this one and this one are always the same irrespective of the truth values of the components, and then we can prove the distributive law as well. I leave this to the viewers as well. However, if you still need help in this one, then you can drop it in the comment box. Now we move to the next law, which is double negation law. This is the sixth logic law that we are doing. It is quite simple and quite logical. Double negation of any propositional statement is the statement itself, which is quite obvious. For example, if P states Sam is smart, negation of P is Sam is not smart. And what is the double negation of P? Obviously it is Sam is smart. Thus, this is the double negation law, that the double negation of a propositional statement is always same as the statement itself. Now we move on to the seventh logic law, which is tautology law. Now we had already done tautologies in the previous video. Here we are going to make use of the tautologies. We know a tautology is a propositional statement that is always true irrespective of the truth value of its components. So the tautology law states that P and a tautology is logically equivalent to the statement itself. That means where P is any propositional statement, if P and any tautology is logically equivalent to the statement itself. Let us consider an example. Suppose we have a statement P which is true or false, and we have another statement Q which is again true or false. What is negation of Q? FT. Now, what is Q or not Q? It is true, always true. Thus, this is a tautology. Q or not Q is a tautology. Now, what is P and Q or not Q? What is it? True together, one of them is false. Thus we see that the truth values of P and Q are always same irrespective of the truth value of its components. Thus we can say that P and Q or not Q, where this is a tautology, is logically equivalent to P itself. Now the contradiction law is almost the same. What does it state? P or a contradiction is logically equivalent to P. Again, let us consider the same truth table as before, P, Q, negation of Q. And now we will consider Q and negation of Q. Now, what is Q and negation of Q? It is always false, right? So, Q and negation of Q is a contradiction in this case. Now, what is P or Q and negation of Q? Just reversing the signs. P or this one. True. In the first case they are true because one of them is true, and in the second case they are false because obviously both of them are false. Thus we see that the truth values of P and P or Q and not Q, where Q and not Q is a contradiction, is logically equivalent to P. Thus we can write it as this, where this is a contradiction. With this we are done with the contradiction law as well. Now we will move on to laws that involve the use of conditional statements and biconditional statements. So the ninth logical law that we will do is also known as the conditional law. The ninth logic law is the conditional law. What does that state? P implies Q is logically equivalent to negation of P or Q. To prove this law, firstly we need to learn the truth table of P implies Q. It's quite simple. Remember, we are saying that if P happens, then Q will also happen. We are not saying anything about what will happen in case P does not happen. So we take the benefit of the doubt, and if P does not happen, no matter Q happens or not, the truth value of P implies Q in that case is always true. Let's make it more clearer. Suppose, what are the possibilities? True together, false together, T, F, T. Now, here in the first case, P has happened and so has Q. Thus, P implies Q has also happened, and obviously it is true. In the second case, P has not happened. It was told to us that if P will happen, Q will happen. Nothing was told to us about what will happen if P does not happen. Hence, we cannot arrive at any possible conclusion if P does not happen. Thus, giving it the benefit of doubt, we assign it a true value because P did not happen in itself, so we give it a true value. Here, P happens, but Q does not happen. Thus, P implies Q becomes false because if P happened, then Q was supposed to happen as well. But since Q did not happen, so we give it a false value. Here, P did not happen, but Q happened. But again, nothing was told to us what will happen to Q if P does not happen. So again, we give it the benefit of doubt and we assign it a truth value. This is how it works in the court of law as well. So using the same logic, if it is given that P did not happen, then we assume that P implies Q is also true. So these two are highly important that we need to know. So now we have learned the truth table of P implies Q. Now in the same truth table, let's add negation of P, which is F, T, F, T. What is negation of P or Q? It is true because one of them is true, false because both are false, and true. So what do we see? The two statements, these two, are logically equivalent because of the same truth values. Thus, we arrive at the proof of the conditional law. Now, the conditional law can also be stated as negation of P and negation Q. This is simply by applying De Morgan's law, which is the very first law that we had learned. So P implies Q can be written as this, as well as this if we just simply apply the De Morgan's law to this statement. So we are done with the conditional law. Now let's move to the 10th logic law, which is the contrapositive law. Now what does the contrapositive law state? It states that P implies Q is logically equivalent to negation of Q implies negation of P. This can again easily be proved with the help of truth table by showing P implies Q has the same truth values as negation of Q implies negation of P. So this is a very simple contradiction law, contrapositive law. The 11th logic law that we will do is the biconditional law. What does the biconditional law state? It states that P, if and only if Q is logically equivalent to P implies Q and Q implies P. We can again prove this with the help of a truth table. Suppose P, Q. P if and only if Q. First we need to as P. Q occurs, P occurs, true. Q does not occur, give it benefit of doubt. Q does not occur but P occurs, give it the benefit of doubt. Q occurs but P does not occur. So this statement is falsified and we give it a false value. Now applying the AND sign here, let us say this is phi and this is psi. So to phi and psi we apply the AND connective. True together, false, false. Now we are considered with this one and this one. They have the same truth values irrespective of the truth values of their components. Thus we can say that these two statements are logically equivalent and hence we arrive at the proof of the biconditional law. With that we come to the end of the conditional laws. I'll just give an example to show how we can use the logic laws. For example, prove P implies Q and Q implies R is logically equivalent to P or Q implies R using logic laws. Now how will you make use of all the logic laws that you have done? Firstly, you need to learn all the logic laws by heart and then you can prove these statements. Here, which logic law can we use? For the first one, LHS, we can write it as negation of P or Q and negation of Q or R. Which law are we using here? Conditional law, right? Now, what can we do next? Here, we can now use the distributive law. But first I'd like to point out an error that I did. This is going to be R. Right. So now it's correct. Now we will use the commutative law. And this can be written as R or not P and R or not Q using the commutative law. Now, which law can be used here? This is a very important step. We see that the distributive law has been used in this case. How can this be written? This can be written as negation of P and negation of Q for R. It can be written as R or negation of P and negation of Q using the distributive law. You see, if you use the distributive law to this one, you will get R or not P and R or not Q. So here the distributive law was in the expanded case and now we are bringing it back to the original case. So this is what we get. Now we will use our very first logic law, which is the De Morgan's law. R or negation of P or Q DML, right? Negation of P or Q is not P and not Q, which was given to us here. So we use De Morgan's law here. Now again we will use the commutative law and arrive at this. Now again we will come back to the conditional law and arrive at P or Q implies R using conditional law. LHS equals RHS, and hence we arrive at a proof. So this is how we will be required to use the logic laws. So if you have any doubts, then please drop them in the comment box and I'll surely reply to them. Thank you.